Good day, dear friends. Here we have an exciting problem related to an accelerating wedge block system. This is a wedge having a rough inclined surface with an angle of inclination theta. There is a block of mass m. If the wedge remains stationary or has zero acceleration, the block will slide down the inclined surface because the angle of inclination is greater than the angle of repose. You have got a term, the angle of repose. What is angle of repose? The angle of repose is the maximum possible angle of inclination for which the block can just be prevented from sliding down the inclined surface. It can be proved that the angle of repose is equal to the angle of friction. Again, you've got a term, the angle of friction. What is the angle of friction? Well, let it be a surface. It is a block, and the surface exerts on the block a normal force, say N. Let the limiting static friction be F. The resultant of the limiting static friction and the normal force is R. The angle that the normal makes with the resultant of the limiting static friction and the normal force is the angle of friction. It is often denoted as lambda. Now, tan lambda is equal to the limiting static friction divided by the normal force N, and the ratio of the limiting static friction to the normal force is the coefficient of static friction, which is denoted as mu s. Let the coefficient of static friction between the block and the inclined surface of the wedge be mu s. Let the minimum horizontal acceleration of the wedge for which the block can just be prevented from sliding down the inclined surface of the wedge be a minimum, and it is directed to the right. Let us now analyze all the forces acting on the block. There are several forces acting on the block. First, the force of gravity. It is denoted by W, and W is equal to the mass of the block multiplied by the acceleration due to the Earth's gravity. The pseudo force experienced by this block is denoted as F, and F is equal to the mass of the block multiplied by the acceleration of the wedge, A minimum. Now, let's analyze the components of the forces along the direction normal to the inclined surface. The component of the force of gravity in the direction normal to the inclined surface is W1. The angle between the normal to the inclined surface and the vertical is also theta. So W1 is equal to W cos theta is equal to mg cos theta. The component of the pseudo force in the direction normal to the inclined surface is denoted as F1, and F1 is equal to F sin theta. Why? The inclined surface makes an angle theta with the horizontal, and so this angle will be 90 degree minus theta, and so F1 is equal to F sin theta is equal to M A mean sin theta. These two components, the sum of these two components are balanced by the normal force exerted on the block by the inclined surface, and so the normal force N can be given as N is equal to W1 plus F1 is equal to, in place of W1 we can write mg cos theta plus, in place of F1 we can write M A minimum sin theta. Now let's analyze the different forces and the components of forces along the inclined surface. The component of the force of gravity along the inclined surface is given by W2 is equal to W sin theta is equal to mg sin theta. The component of the pseudo force in the direction parallel to the inclined surface is given by F2, and F2 is equal to F cos theta is equal to M A minimum cos theta. There is another force which is the static friction, and it acts opposite to the direction in which the block tends to slide down, and so the frictional force acts up the inclined plane, and let it be small f, and the frictional force, it is a limiting static friction, F is equal to the coefficient of static friction mu s multiplied by the normal force. is equal to mu s. In place of normal force, we can write this expression mg cos theta plus ma minimum sin theta. Since the block has zero acceleration, or it is stationary relative to this non-inertial frame of reference in the form of the wedge, we can say that all the forces and the components of the forces acting along the inclined surface will be at equilibrium. So the sum of F and F2 will be equal to W2. Thus we can write here F2 plus F is equal to W2. In place of F2, we write M A min cos theta. In place of F, we write this expression mu s mg cos theta plus m a min sin theta is equal to, in place of W2, we write mg sin theta. And from this equation, we can easily get the expression for A minimum, and thus we have the minimum acceleration, horizontal acceleration of the wedge directed to the right is given by A minimum is equal to sin theta minus mu s cos theta divided by cos theta plus mu s sin theta multiplied by the acceleration due to the Earth's gravity. Now, in place of mu s, we can write tan lambda. Lambda is the angle of friction. If we write, we get sin theta minus tan lambda cos theta divided by cos theta plus tan lambda sin theta is equal to, now let's multiply the numerator and denominator by cos lambda. What do we get? Sin theta cos lambda minus cos theta sin lambda. Sorry, here we have got to give the g, the acceleration due to the Earth's gravity. Cos theta cos lambda plus sin theta sin lambda multiplied by g is equal to, in the numerator we get sin theta minus lambda, and in the denominator we get cos theta minus lambda, and sine theta minus lambda divided by cos theta minus lambda is tan theta minus lambda multiplied by g. This is a simple expression and easy to remember. This is another expression. If we cannot remember it, we can easily remember it at least. Now, if there is no friction, if the inclined surface of the wedge is frictionless, then lambda will be 0. In that case, A minimum will be tan theta multiplied by the acceleration due to the Earth's gravity. And this very expression was obtained in the last video. Now, in the next video, we'll have another expression for the maximum horizontal acceleration of the wedge, for which the block can just be prevented from sliding up the inclined plane. And wait for that. Thank you.